I'm Sukjin from Seoul National University, currently pursuing my master's degree under Professor Jinho Lee. Today I'll be presenting PathWeaver, a highly throughput multi-GPU system for graph-based approximate nearest neighbor search. I'd like to start briefly introducing what ANS is. Approximate nearest neighbor search is widely used in search engines, retrieval augmented generation, and computer vision to quickly find the most relevant point for a query. Graph-based ANS connects relevant data into a graph, reducing the search space and enabling fast querying. And GPUs with high bandwidth and many compute units are well suited for high throughput ANS. However, as global data has grown, databases have become too large to fit into a single GPU, creating a major challenge. To solve this issue, we present PathWeaver. PathWeaver is a highly scalable multi-GPU ANS solution by introducing inter-shard connection, pipelining, and ghost staging for scalability, and utilizing direction towards the query to reduce unnecessary traversal. In this section, I will explain the background of our work. First, we focused on graph-based ANS process. Second, data parallelism for multi-GPU ANS to handle data sets beyond the size of single GPU. Here, I will explain how conventional process of ANS works. During the build stage shown on the left, we connect close data points with edges. This process is applied to all nodes, constructing a highly connected graph. And this pre-built graph is used during the search stage, as shown on the right. By traversing the graph and moving towards the query, the search algorithm finds the data point closest to the query without scanning all the data points. Now I will explain the existing search process in more detail. On the left, the search starts from a random node. Then we examine the neighbors of the current node to find the one closest to the query, which becomes the frontier of the next iteration. By repeating this process, we gradually move closer to the query, ultimately finding the data point closest to the query. Next, I will explain the conventional process of multi-GPU ANS. In multi-GPU ANS, during the build stage, the dataset is randomly partitioned into multiple shards, and each shard builds its own independent graph. At search stage, each GPU independently traverses its assigned shards using the same graph-based search process we discussed earlier. Then, each GPU finds a local result within its local shards. Finally, the CPU merges the result to determine the global result. To summarize, I'll explain how data parallelism works when processing multi-queries on a conventional multi-GPU system. In this setup, the same batch of queries is broadcast to all GPUs, and each GPU independently searches within its own shards. In the same way, query 1, 2, and 3 are processed sequentially. The CPU merges this result after searching in all of the queries, all of the GPUs. Now let me explain the motivation of our work. First, existing multi-GPU ANS solutions show low scalability, not fully utilizing added GPU efficiently. Second, there are frequent unnecessary node visits during the search, leading to wasteful computations. Starting with the first motivation, the low scalability, here's an example of search process on a 4-GPU system. We see that a single GPU inside the 4-GPU requires a total of 3 iterations to complete the search. However, when we examine all 4 GPUs, each GPU independently searches on its own graph. Even though we use 4 GPUs, the search now requires a total of 12 iterations to complete the search. Eventually, both single GPU and 4 GPU needs 3 iterations per GPU. This example shows that there is a redundant graph traversing due to independently built graph. Next, let me explain our second motivation, frequent unnecessary node visits. This is an example of node discard on a single GPU search process. As explained earlier, the process starts from a random starting point. Then we calculate the distance between the neighbors and the query, and uses the closest node as the next frontier. In this process, nodes that are far from the query are discarded. This phenomenon occurs in every iteration, resulting in frequent unnecessary node visits, which are highlighted in pink. This triggers unnecessary overhead during the search. Given these motivations, I'll explain the 3 schemes of PathWeaver. The first motivation is low scalability. caused by redundant traversing in independently built graphs. To address this issue, we introduced pipeline-based path extension, which connects adjacent graph to path results. And we also introduced ghost staging, which adds a small graph before the first stage. Next, the second motivation is unnecessary node visits. In more detail, most of the explored neighbors are discarded. And to reduce unnecessary node visits, we propose the direction-guided selection, which selects the neighbors aligned with the query. Let me start by walking you through the details of pipeline-based path extension. First, in pipeline-based path extension, GPU 0 follows the original search process. In this example, three iterations are needed. After GPU 0 completes the search, we use inter-shard map, which maps the final result in GPU 0 with starting point of GPU 1. Now, instead of GPU 1 starting from a random starting point, it starts the search from a closest node to the query. Without this information, the search on GPU 1 starts with a random starting point, finishing in 3 iterations. However, by finding the close starting point, thanks to inter-shard map, we now need only 1 iteration. And now I'll explain the preprocessing of inter-shard map. We first find the closest point in GPU 1 from every point in GPU 0, and construct a lookup table, noding GPU 1 as a key and the corresponding closest point of GPU 1 as the route value. This allows immediate retrieval of the corresponding closest starting point. Now, let me explain how pipeline-based path extension is applied to an example of 4-GPU system. In the existing multi-GPU system, every GPU processes the same query. However, in pipeline-based path extension, we rearrange the query in a pipeline manner. This allows query to be processed sequentially through GPU. For example, query 0 is sequentially processed by GPU 0, 1, 2, and 3 before finally reaching the CPU for merging. During this sequential process, we apply inter-shard map. To pass local result produced from a previous GPU to the next GPU. Let's go into more details of what is happening in each stage. First, each GPU starts with a different query. Then in the first stage, each GPU processes the search in its local graph using the original procedure, as an example which requires 3 iterations. After completing stage 1, each GPU now finds the local result within its graphs. Then now each GPU processes the next query. As we can see in the left figure, GPU 1 is searching for query 0 now. By applying inter-shard map, each GPU passes the result to find the closest starting point in the next GPU. As depicted in the left figure, from the red local result from GPU 0, the search on GPU 1 starts closer, highlighted in blue. In stage 2, the search benefits from the previous search result, reducing the number of iterations to just 1, which reduces the execution time in stage 2. After stage 2, again, each GPU processes the next query. And this time, GPU 2 processes query 0 and also benefits by the result passed by GPU 1. The same goes with stage 4. Finally, every query proceeds through all GPUs, and CPU merges all the results. To summarize, execution time of stage 2 to 4 is reduced by the previous search results. However, the first stage does not have previous information, resulting in relatively slower execution time. To address this issue, PathWeaver proposed ghost staging, adding a small graph before the first stage, applying a type of hierarchical solution just for stage 1. During the preprocessing stage of ghost staging, we extract a small subset of nodes, and then build a small representative graph. This lightweight graph is used to quickly guide the first stage. In the search stage, without using the small representative graph, as an example, it takes 3 iterations to finish the search. Instead, when we use ghost staging, we start the search on a representative graph, which is much faster than the full graph search. And small graph passes the result to the original graph, which provides a closer starting point. Benefiting from the result passed from the small graph, the search only needs a total of 2 iterations. Now let's see where we left off from pipeline-based path extension. The first stage does not have previous information, resulting in relatively slower execution time. Now, when applying Go staging, every graph in each GPU has a small representative graph. The first stage now starts on a representative graph. And then representative graph then passes the result to the original graph. Finally, the search on the original graph. Thanks to the result from the representative graph, search of the original graph starts closer, reducing the execution time of stage 1. Now let me summarize where we are. So far, we addressed the low scalability issue using 2 methods. Yet, redundant visits still dominates the search. So to address this, PathWeaver introduced direction-guided selection. As we discussed in the motivation section, most of the neighbors are quickly discarded, which are highlighted in pink. However, there is a clear pattern in the useful neighbors. For example, in the first iteration, node 3 is the closest node among the neighbors and used as the next frontier. And it has the smallest angle between itself and the query among the neighbors. This applies to iteration 2 and iteration 3. Motivated by this observation, we can select aligned neighbors before calculating the distance of all the neighbors from the query. In the pre-processing step of direction-guided selection, we use an n-dimensional vector in each node. By subtracting the source and destination, edges can be expressed as a n-dimensional vector. And then we compress the edge vector into 1-bit representation, positive value as 0 and negative value as 1. We utilize this compressed edge vector to effectively select neighbors aligned with the query. I will now explain the detailed process of single iteration in a search process when using direction-guided selection. First, the search starts at a random point. We then load the compressed edge vector to compute the cosine similarities between the edges and the query. Next, we select the top 2 nodes best aligned with the query. Only after selecting the promising neighbors, we load the full node vectors and calculate the exact L2 distance of the selected top 2 nodes. Finally, finding the closest node. As shown in the red box, this filters unnecessary node vector loads. Giving a little bit more detail in each step, to calculate cosine similarity using compressed edge vectors, which is a small red vector, we first make 1-bit direction vector pointing from current node 0 to the query, and use bitwise XOR operation and counting non-zero values, we calculate the approximate cosine similarity. Next, to select the best aligned nodes, we sort these cosine similarities and find the highest tuned edges. After that, for the selected promising nodes, we load the full node vector, which is the long light blue vector, to calculate the precise L2 distance. And finally, finding the closest node. After applying pipeline-based path extension and Go staging, total number of iterations has decreased. However, each iteration has unnecessary node visits. By using direction-guided selection, in every iteration, irrelevant neighbors are filtered out. And this reduces the execution time across all stages. Finally, I will share parts of the evaluation on PathWeaver. The main results were obtained using 4 RTX 6000 GPU connected by NVLink bridge. We evaluate the performance using 6 different datasets with vector dimension ranging from 96 to 960 and dataset size from 1 million to 50 million. We use 3 baselines, Kagra, state-of-the-art GPU solution, and we extend it to support multi-GPU settings. GGNN, best of our knowledge, the only baseline supporting multi-GPU settings. And finally, HNSW, CPU solution leveraging hierarchical graph. Now, let's see how much PathWeaver accelerates search process on multi-GPU settings. In this evaluation, we measure query per second while ensuring high recall of 95%. PathWeaver achieved 3.24x speedup over Kagra at high recall of 95%. Most notably, on the wiki 10 million dataset on the right, PathWeaver achieved 5.3x speedup at 95% recall. Next, we evaluate the effectiveness of pipeline-based path extension. And 95% recall, shown on the left side, applying pipeline-based path extension leads to clear performance improvements. And the target recall of 97% still demonstrates consistent speedup. We also compare the impact of recall degradation of direction-guided selection. Compared to exact calculation, using 1-bit compression showed slight recall drop of 0.3%. However, using a random selection resulted in significant recall drop of maximum 3.8%. This indicates that direction-guided selection successfully identifies critical nodes without degrading overall accuracy. In conclusion, PathWeaver is a highly scalable multi-GPU ANS solution proposing inter-shard connection, ghost staging, and direction-based neighbor selection. PathWeaver outperforms state-of-the-art GPU baseline by 3.43 times better performance. We also open source PathWeaver code. For details, please refer to the paper. Thank you for listening till the end. If you have any questions, please let me know.